Hello, my name is Titus Studden. I'm here working on Project 4 for CpE 3110, and this is our first circuit here. This is a RTL point-to-point transfer system that is using multiple registers, which are using control signals to send from one register to another register to another register. And to ensure that the registers maintain their data, I have an else statement saying that if something isn't being sent, it'll just route it back to itself so no data loss occurs. And that's pretty much all that's happening here. This is just the register logic for each one. And if we move to the wave diagram, you can see that our data in is here, and we set the load A high, which would be register 0. It goes into register 0, register 1, register 2. Let's see, what did I do here? I changed the data in here and then just parallel loaded it to all of them. So moving on to Quartus, you can see this is the block we have here. It's kind of a whole mess just because of all the individual sending signals. And here, unlike the previous project, I had the time to take the clock, run it through a counter so that I could take the, I believe it's a 50 megahertz clock, and I just ran it through a high bit counter to pull that down to something actually observable. Moving to the RTL, we can see that it uses a ton of selector muxes paired with registers. So nothing too crazy here either. Moving to the hardware testing, you can see this blinking light is the clock. I ran it to an LED so that I could actually know that it's working. So what I will go ahead and do is I will load our first register with 1 bit. You can see it runs up here, and then I will take that first register and I will run it to our second register, and then I will run that to our third register, and then I can reset it and do the same thing and send it to all of our registers once again. And then what I can do is I can put this at reset and I can run all 3 of these high, and they all load in at the same time. And that's pretty much the gist of this circuit. Over here on the oscilloscope, we can see that after hooking it up to the clock, I got a 650 millisecond time delay. And that is everything for this circuit. Okay, this is circuit 2 in project 4. This is a point-to-point RTL transfer using a bus instead of just going from one register to another register to another register. We have a uniform bus that they all sit on. So here is the tri-state logic, the tri-state buffer, saying that if the reset's high, then the bus is 0. If data to bus is high, then it's data in. Register 0 to bus, it's register 0. Same for R1, R2, else it is Z-stated. This also unintentionally creates a priority list where data in is the highest. But then moving on to the register logic, it's just saying that if it's reset, all the registers are this, and then if load, it'll take the bus data and run it to the register. So nothing super complicated here. Moving over to the waveform diagram, we can see that right here we have our 001. We load A, we load B, we load C. Well, this is our bus out. This is an observation point. So load A, load B, load C. And then we do 011, we can load all of them, we can clear all of them, and then we can go from bus to register 1, and then we can take it to register 0 and 2 at the same time. The nice thing about this is that it takes less switches, but it takes more switches per clock cycle to do the same thing, because you have to have the load signal high and the register to bus signal high in the same clock cycle. moving over to Cordis, this is the block diagram. I did the same thing as the previous one where I have a counter here to slow down the clock. So, but other than that, this is relatively the same as the previous. And if we go to the RTL, it also looks pretty much the same. The only difference is that we have more select lines. We have our reset data bus, ROB, and R2B all here. I believe R1B is also filtered in here. We have our registers with selectors, register, register. So nearly the same thing. Moving over to, let's see, I guess, yeah, hardware testing. So going over here, again, you could see that this blinking green light is going to be our clock. So what I'll do is I'll set the reset high, drop the reset. I will, let me do this for visual clarity. We can set this bit high, and then we will set the bus high. So now it's loaded in the bus, and now I can load this in a register. So this is register 2. Now I can drop this, load it in register 2, drop it, load it in register 0. Now if I reset these, I can load it in register 2, and I can drop this register, drop the bus, so that the register holds its value. And then I would do register 2 to bus, and then I would load register 1. Then I drop register 1, load register 2. And this is repeatable for all of the other combinations. Over on the oscilloscope, after hooking it up to the clock, we can see we have 443 milliseconds of time delay. And that'll be everything for this circuit. Okay, this is the final circuit in Project 4 for CpE 3110. So what we've done here is we are trying to measure the time for the board to pull the memory back. So what's happening here is this first piece of code is, let me make sure I'm on the correct one. This one is writing the data to the addresses and to the SRAM DQ. So it's basically just setting the lower bit and the upper bit and the chip all to low. They're all active low, so it's starting them. And then whenever the write enable, the switch I have on the board, goes high, the write enable will go low. The read enable doesn't really do anything in this moment since the write and read programs are split into 2. But the SRAM DQ is padded 13 zeros. I'm sorry, I'm not quite sure why this isn't focusing. There we go. Then moving over to the read, we can see that it's effectively the same thing, except the only difference is that the data out is based on the read, and it's the board was giving me an issue where it would throw all of the LEDs high, so I had to run it so that it would only show data if the read was high, else it shows nothing. And the rest is pretty much the exact same. Going to the block, again, the border's giving me some issues, so I had to run all the non-used LEDs just to ground so they wouldn't light up, because they were all lighting up and it was really, really confusing. I ran the output to, the input to LEDs so I could see what I was inputting into the memory, and then I have the SRAM DQ and the SRAM address pins all assigned here. Moving over to the other block, this is the same, but here I have it so that the first reading I'm getting is the output enable changing, and then I'm seeing the difference in time between the output enable going off and the memory showing up as the output. So I'm going to go ahead and compile some things just so that we can see the RTL files. See what the compiler thinks is happening. And then we'll go to Tools, Netlist Viewer, RTL Viewer. this is a very simple circuit because all of the computation is happening hardware side. All that this program is doing is determining, control enables effectively. And then we can load up the read and see what that looks like. This is nearly the same, except that the read is determining whether the SRAM is actually making it to the data out. And then of course that read is going to the on. So there's nothing too different about this. It's just that this read is actually determining whether this SRAM is making it to the data out or not. Moving, and I'm not going to show ModelSim because I've shown the code from ModelSim on here. I had to do a lot of changing in Cordis. Moving over to hardware testing. So the read enable, when it's low, there's nothing here. And whenever the read enable is high, you can see that the data I put into the memory channel 2 is loading up. I can load it to memory channel 0, which I loaded zeros into. I can do 1, which I loaded a 1 into. I can do address 3, and I can also do address 4. Now I'm going to show an example. I did not load this value, and this is why I had to have the else z state, because when the read is low, it's not showing anything, and whenever it is high, this bit is lit up for some unknown reason. Likely due to the fact that the memory states weren't reset, it's probably just throwing junk data. Moving on from that, we have the oscilloscope reading, which is giving us 58 nanoseconds. And that's going to be everything for this circuit.